Hi everyone, this is the second video for section 9.3 on real numbers. So in this video, we're going to talk about the last property that we're going to talk about, which is the notion of completeness. So complete just means that there are no holes or gaps along the number line. And so you can see here that whenever we define complete, we say the real numbers are complete because there are no holes or gaps along the real number line. And so if you've noticed, specifically in chapter 8, whenever we do things with integers, we talk about what's called in the book an integer number line. So we have number lines, and we can talk about a different number line for each of the types of number. So there can be a natural number line, a whole number line, an integer number line, a rational number line, a real number line, and that just means that on that number line are only numbers of that type. So the number line that we most often see is the real number line, and it's because, well, that just has all the real numbers. Those are all the numbers that we deal with in everyday life. Unless you go into some STEM field, you're not going to talk about imaginary numbers. So we just typically deal with the real number line. So this real number line just has all of the real numbers. Okay, so the real numbers are complete because if you take the real number line, let's just say that 0 is here, just for some context. If we pick any point on the number line, there is a value there, whether it's rational or irrational, right? Remember that the real numbers are divided into the rational numbers and the irrational numbers. Any point on the number line has a value associated to it. So this could be 0.7 repeating, right? That has a number associated to it. So you may hear this and say, well, that sounds really similar to dense, because dense says between any two numbers exists another number of that type. And we said that you can think of this as zooming in on the number line, specifically the number line of that type. So there's a really subtle difference here, and it has to do with what we start with. So dense starts with a set of numbers. So we can talk about the density of, like we did in the last video, the density of the naturals, the wholes, the integers, the rationals, irrationals, and the reals. We can talk about the density of those number sets. And when we talk about the density of those number sets, what we're doing is we're taking a number line, we're looking at a value A and a value B of that number set. So we're just going to call this set of numbers. We're just going to call this set of numbers S, right? Capital S for set. So we're going to call a set of numbers S. So if we look at A and B as elements of S, we want to know is there a number C in S such that A is less than C is less than B. So this is how we can kind of formalize what we talk about when we say density, is that for all A and B and C, I'm going to actually write this, they are going to correspond with the symbols that are right. So density just means that, well, for any, I don't think we didn't, if I can recall correctly, we didn't talk about the quantifier, so I'm not going to write that. So this says that for any A and B in S, there is some C in S such that C is between A and B. So I recognize this looks really similar to what I just erased. That's okay. So density says if we have two numbers in a number set, then there is a C in that number set, another number in that number set that's between them. So if we have any A and B in the number set, we can zoom in on the number line and put a number between them. So we start with the set of numbers, and then we put those numbers on the number line in some ordering. Whereas completeness starts with the number line and adds values. So density says we have a set of numbers and they're ordered on the number line in this way. And if we zoom in, we can put a number in between any two, right? Where this C, you can think of this C as being placed here. We have this A and B that are already on the number line. We go into the set of numbers, we search for one that's between them, we find that number and we stick it right here on the number line. Whereas completeness says that if you look at your number line, every point on this number line already has a point associated with it. So I think that it's easiest to understand completeness by looking at something that's not complete. So the only number set that we've talked about that is complete is the set of real numbers. The naturals, the wholes, the integers, is the real numbers. My apologies. The only number set we've talked about that's complete is the real numbers. The naturals, the wholes, the integers, the rationals, and the irrationals are all not complete. And you can see that pretty easily. So if we just look at the integers, for example, we have -2, -1, 0, and 1. If we're looking at this number line of integers, well, we can see that there's this space here between 0 and 1, right? We see that there's a space here between 0 and 1. And there's no integers between 0 and 1, right? We talked about this. Well, we can actually look at 1 and 2. So if we just look at 1 and 2, which is the example that we used when we talked about density. -1, 0, 1, 2. There's no integer between 1 and 2. So if we were looking at a number line of the integers, this point here between 1 and 2 at 1.5, it's not defined on this integer number line. And that's because the integers aren't dense. And these are really related, but slightly different. So let's look at the rationals instead. So we can just look at the same number line, but instead we can say this is a rational number line. Because as we know, the rationals are dense, because between any fractions, we can just find another fraction. And we talked about how to do that in the previous video. However, if you think of the number square root of 2, so you should have gone and looked at the proof of why the square root of 2 is irrational. So you should have already done that if you're watching this, and that's important because we're going to use it now. So we know that the square root of 2 is irrational. And remember that the square root of 2 is approximately equal to 1.41421. Something that's like that. So we know that that number on the number line is somewhere between 1 and 2. So this point on our number line can be, I'm actually going to do it in blue. This point on our number line can be associated to square root of 2, that point on our number line. However, this number isn't on the rational number line because it's an irrational number. So this tells us that the rational numbers are not complete, because there is this point on the number line that corresponds to square root of 2, but we don't have a rational number at that point because the square root of 2 is irrational. So this is why Q is not complete. However, the real numbers are complete because at any given point on the real number line, you're at either a rational or an irrational number. And because those are the only two options and all of those are part of the reals, that's why the reals are complete. It's because you combine rational numbers and irrational numbers, and you have everything you would want to. So I hope that this sheds some light on what it means to be complete. The concepts of density and completeness are pretty complex. So if you need to ask questions about them, please do. Yeah. So this is density and completeness. So I think that the next section talks about famous irrational numbers, pi and phi and e. So I'm going to save that for the next video.